numerous lectures on astrophysical objects of various types. The emphasis in the two lectures today will be on plasma processes that I consider fairly universal and are underlying the physics of many of these objects that you've already heard about. Magnetic reconnection is one of them. For those of you who do not know me, I'm Amitava Bhattacharjee. I teach in the Department of Astrophysical Sciences at Princeton University and serve as head of the theory department at the Princeton Plasma Physics Laboratory. You're all within 60 miles of Princeton, so I hope you will come and visit during your stay. And if you want to come by and visit PPPL and Princeton, please let me know, and I'll arrange for you to come and visit. I know many of you already know or have heard of magnetic reconnection, but I'm going to try and presume nothing and start from the very beginning. And if there is any question that any of you would have, please stop me. So, what is magnetic reconnection? I should not make an apology for showing you equations. I'm a theorist by training. These are the tools of the trade. And so, unapologetically, I'll be using equations, but I hope I'll explain what these mean. And I think many of you are familiar with this in any case. If a plasma is perfectly conducting, that is, it obeys ideal Ohm's law, and you've seen this by now, right? E plus V cross B over C equal to 0. This is the ideal Ohm's law in the MHD model, where there is no non-ideal effect. E is the electric field, V is the velocity of the plasma thought of as a single fluid, B is the magnetic field permeating plasmas, and C is the speed of light. The consequence of this important equation is often codified by what is called Alfvén's theorem. For many of you who know about this already, Hannes Alfvén is regarded as the father of magnetohydrodynamics and is the only plasma physicist who has ever won the Nobel Prize. He richly deserved it, but there's always a standing joke in the particle physics community. That's because he was from Sweden, which I assure you has no foundation whatsoever. He fully deserved it, as do many plasma physicists, but that's another story. The consequence of the frozen in flux condition is what is called B lines are frozen in the plasma and no reconnection occurs. But as I said, this is codified often in the form of theorems, which I will say. Do I have a pointer? Actually, somebody just asked me if I would use a pointer, and I said no, but now I think I should.
We have this hole here to point it.
Oh, okay, that's fine. So it can be stated in one of two forms. One is that suppose if you have a moving plasma and you draw a circuit C1 and wait a very small period of time, and if you think of this being threaded by plasma elements, all of which are moving according to the equations of MHD, it deforms very quickly into a circuit like C2. And if you wait long enough, it will deform even more so. But our point can be made by simply saying, according to Alfvén's theorem, the flux threading this initial circuit element, B dot dA over this circuit element, remains invariant during the motion of the plasma. An equivalent way of stating the same thing, and one of the other implies the other formulation, is that suppose if you have a line which passes through two plasma elements, and imagine that this is actually a magnetic field line, which for simplicity has been assumed to be straight, but that's a totally unnecessary assumption, just drawing for the sake of the figure. So if two plasma elements lie on a given field line and the plasma motion occurs, the other version is that if you have these two plasma elements will remain on that particular field line for all times as beads in a wire. So magnetic fields are like wires to which plasma elements are tied as beads. And if, in fact, the plasma is ideal, these two elements will remain on the wire for all times. This is often a statement of magnetic field lines being frozen in the plasma that you've seen talk about in textbooks. What reconnection does is to break Alfvén's theorem. And that can be done by putting on the right-hand side a quantity R, and a working definition of reconnection is if the curl of that quantity is non-zero, then Alfvén's theorem will be violated. Not R by itself, but the curl of R. What happens under those conditions is, this is a fancy word, if you have two loops in a plasma, in an ideal plasma, field lines which are knotted like this, they will remain knotted for all times if the plasma is ideal. That's what I mean by saying there can be no change of topology. They can deform and do whatever they like, but they cannot break their knottedness. There are rigorous ways to prove these things, and it's there in the literature, but that's what people mean by ideal topological invariants. And in an ideal plasma, there are an infinite number of them, and an uncountably infinite number of them, otherwise referred to as denumerably infinite. But if on the right-hand side you don't have zero, but the curl of a quantity which is non-zero, then you can break that theorem. And field lines can reconnect. And when can this occur? This can occur in a whole variety of ways, either through collisions or even in collisionless plasmas. And as I will talk about as the lecture proceeds, R can contain all sorts of non-ideal effects: resistivity, Hall current, electron inertia, and pressure tensor, all of which violate curl of R not equal to zero. Question: if it is just the gradient of pressure, scalar pressure, can it break field lines? The answer is no. I heard it said, because the curl of gradient of pressure is zero. So in fact, sometimes in Ohm's law, you have a correction term, which is gradient of pressure by density. And if you make the assumption that density does not change, then the curl of that term is zero. Even though it is there and can contribute to the electric field, it actually does not break field lines. On the other hand, if the pressure is a tensor, curl of the divergence of a pressure tensor is not necessarily zero, and that can break field lines. And this is an important effect in collisionless plasmas, as you must have heard yesterday from Lorenzo and Sasha, is that they do a lot of relativistic particle in cell studies, and their reconnection occurs as well. Well, there's no resistivity. How does it occur? Through one of these mechanisms. So this is a cartoon that is often shown, field lines coming, and this is somewhat of a special point, but before reconnection it looks like this, after reconnection it looks like that. This sort of breaking and reconnecting is what is often cartoon-wise described as reconnection. And as you know, the reason why this is a process of great interest, because the universe presents us with a great reservoir of magnetic energy, which in an ideal plasma is hard to release. Through ideal dynamics in the system, you can go from a higher to a lower energy state, but that energy conversion is so much more efficient if you actually have dissipation in the problem. Why? Not just because energy decays in a dissipative system, but because reconnection enables topological reconfiguration of field lines in such a way that you can have access to minimum energy states that you cannot have if the plasma is ideal. And that can produce enormous amounts of energy that ideal relaxation does not let you. An example of this, and there are 2 points I want to mention to you by showing this picture, is that as we proceed in this work, you will see that we will spend some time on resistive MHD reconnection. And what happens in that is that E plus V cross P over C is actually equals eta J. eta is the resistivity, J is the current density. If you take the curl of that, it's non-zero, right? Because even if eta is a constant, curl of J gives you, by Maxwell equations, a non-zero term. So you can ask yourself, if I have a non-zero term on the right-hand side, is that enough? Well, suppose you have a metallic conductor, right, which has finite amount of resistance. And you put a magnetic field there, and if you have electricity and magnetism, you've done it, then you know that magnetic field lines will diffuse in the system. So what is the difference then between simple diffusion or dissipation and reconnection? A crucial ingredient that is often overlooked is that geometry or topology plays a critical role in reconnection. And here I give you an example of that. This is a classic two-dimensional geometry where reconnection is supposed to play a very important role. So when you look at this picture, what is the thing that strikes you about the B field at the outset? Look at the top picture. Is it the simplest thing you could think of in terms of magnetic fields? Is it? Let me contrast that with a magnetic field that is just straight everywhere, pointing in the same direction. That also is Maxwell's equations, right? This is a little different, isn't it? Because the field lines are pointing in opposite directions across a surface here where it goes to zero. This is a classic configuration of reverse fields that is a requirement in laminar reconnection. What happens is in these systems that if you actually impose a sinusoidal perturbation, you can get structures like this. So I have a straight magnetic field pointing in opposite directions. The tan hyperbolic function has that property, for example. It's -1 here and +1 there and connects up. If you impose a sinusoidal perturbation on top of that magnetic field, you get structures like this. This has a very different topology than this. Why? Because at this region, in this region, which is called the neutral line, where the B actually vanishes before it turns over, you're beginning to get cat's eyes type of structures where some of the field lines are closing on themselves. And then there is a separatrix, which is again pointing in this direction here and that direction there. But in between, there are these new kind of objects embedded where they've closed on themselves. Well, when you started out with this configuration, you didn't have these. There's topological change. Can an ideal plasma do this? The answer is no. So suppose if you try to do a calculation where you put in a sinusoidal perturbation and you push the equations of MHT through to figure out how that perturbation evolves in time. And I did this exercise. It takes a few pages of algebra to do just to prove to myself that ideal MHT really works. That if you do not have dissipation in the system, but if you try to brute force a calculation, you will quickly find that the time-dependent equations of resistive MHT are going to tell you that perturbation must go to zero. There is nothing in ideal MHT that will support a sinusoidal perturbation that will break the topology of field lines to produce this structure. So the mathematics tells you what intuition tells you as well. You look at this structure and you say, there is a change of topology. How do I know that Alfvén's theorem is going to tell me the same thing? Try Alfvén's theorem, put that component in, turn the crank, and have eta go to zero, that component is going to go to zero. So in other words, in an ideal plasma, you could not support or sustain that sinusoidal perturbation that breaks up these field lines to form islands. These are referred to as islands. Do you understand me now? So this is a very ubiquitous thing. You look at many simulations and you'll see these islands appear when you're doing dissipation problem. In fact, the classic work in this area was done by Harold Firth, Marshall Rosenbluth, and John Killeen in a classic paper in the 1960s, where they actually discovered what so-called resistive instabilities were like. And they went through this calculation, and it's a wonderful paper, but very hard to read because they were using boundary layer techniques that are used in hydrodynamics to solve this class of problems. The other place where this shows up is in hydrodynamics, the equations that Pascal talked to you about. And you remember that there was, in fact, Navier-Stokes equation that she derived, right? From Navier-Stokes, if you take the curl of Navier-Stokes, you get a vorticity equation, which is very similar to this. So the vortex reconnection problem is very analogous to the magnetic reconnection problem in plasma physics. It just is that in plasma physics, there are some subtle differences that I won't go into, but the literature is a lot more well developed in magnetic reconnection than it is in vortex reconnection. Some of these issues are technical, and some of these issues have to do with where people's interests lie. But you now know that you have this. So there's one point I want to make. I raised this issue. What would happen if you had reverse fields? You didn't have this, but you had field lines pointing all in the same direction, and you had resistivity on the right-hand side of Ohm's law. What would happen? Well, something will happen. The field will decay, right? But what sort of a time scale would it decay on? Typically the resistive time scale, which is slow and long. So it makes a great deal of difference what the topology is. If the field lines all point in the same direction, they diffuse. But diffusion is different from reconnection. As you will see, and I'll demonstrate in class, that reconnection occurs on a time scale much more rapid than diffusion. And the key ingredient that separates whether you get diffusion or reconnection is topology. It's sometimes underemphasized. You know, people think you throw some dissipation on the right-hand side of Ohm's law and run these simulations. And complicated simulations have complicated things going on. Some places things diffuse, in some places things reconnect, and they're often jumbled together as one. But be careful on what you call reconnection. Well, these are not just in the theorist's imagination. You know, NASA flies missions. And out there, Justin Casper is here, and as you know, he is a principal investigator on the Parker Solar Probe mission, which will actually go as close to the sun as any, I mean, will go the closest to the sun as any. Not as close as this cartoon would show to you, but they're getting quite close, where they begin to see coronal structures. And I hope you'll hear lectures from him in the next couple of weeks on what we are learning. And he's learning astonishing things. But before he did this, even as a motivation for what is called the magnetosphere multiscale mission, people were looking at coronal loops, and this is magnetic field lit up, and it's an X-ray picture, if you will. And people do think of large-scale island structures such as this, which could be one possible explanation of this. This is a cartoon, this is a simulation, and people try to suggest that the evidence in the sun is that. But actually, this is not founded on, why is my movie not running? What a pity, because it's a really beautiful movie. It's showing up. Media not found. Okay. If you go to the Solar Dynamics Observatory, what you will find is that what this shows is a beautiful erupting loop that evolves from the surface. And what you will see in that movie, this is, by the way, an image of extremely high resolution. I wish I could show it to you. It's not a theorist's imagination. This is measured. In astrophysics, we often have very beautiful pictures for which it's hard to get movies like I was about to show you. But this is actually seen, detected, and I'm sorry to just point to you this with no activity there, but there's a beautiful loop that gradually forms and erupts and goes out. And the separation of the loop from the surface requires things to pinch off that require reconnection. That's something that occurs in the flaring sun. In the Earth's magnetosphere, which, by the way, is of interest to you, to even those who study pulsars or people who study terrestrial magnetospheres at places other than Earth, like Mercury, for example, or in some of Jupiter's moons. What you have is the sun and the solar wind, which impacts the Earth's magnetosphere. And so, if you abstract it down to a cartoon, what you will see here is the solar wind comes. This is the Earth's dipole field, goes from north to south, the magnetic north to south. And if you have a solar wind, often referred to as an interplanetary magnetic field that points southward, then you could actually have reconnection occurring between the field that points upward and the field that is pointing downwards. Issue of topology, you form something like an X point that then allows flux to be transferred to the night side. They call it the night side because the sun is here. The Earth stands in between, and the other side of the Earth, you have the plasma sheet. That flux leads to the thinning of the plasma sheet, and you can have reconnection going on out here just as you could have it going here. And in both places, during southward turning of the interplanetary magnetic field, reconnection potentially occurs because you're looking at field lines that are actually pointing in opposite directions. There's a lot of measurements. In fact, one of the wonderful things about the magnetosphere is that there's years and years of local measurements of magnetic fields and flows that people have to make sense of. So the theories are highly constrained. You cannot get away doing anything because too much is known. And so it is really possible to rule out theories. And when you can do that, you have ripe ground for controversy because everybody who loves his or her theory says, no, my theory is right, and the other person says, no, there's real data. So they can go back and forth on what the data actually means. So it's, in that sense, not as harmonious a field as astrophysics sometimes tends to be, where there is scarcer observations in some areas and 10 theories can live together. Because it's not yet quite precise enough to rule things out. Sometimes it is, but sometimes it is not. So I wanted to give that to you in the way of background, and now I want to take you back to how reconnection theory actually came about and what were the various things that were actually driving it. So there are two classes of problems in reconnection. It's a linear instability when you have a geometry like the one that I showed you. And the question that you automatically ask yourself is, what happens when this instability is going nonlinear? Now, the way in which the field evolved is that you have to look at the whole stretch of the field, spanning laboratory fusion plasma physics, space physics, astrophysics, and put a whole picture together. Because depending on the questions that people were asking, different people went at different aspects of the problem. This whole question of taking a reverse magnetic field configuration and having it break up into islands was driven, first of all, by the laboratory plasma people who saw that even after they had stabilized a plasma for all ideal instabilities, things were still happening. So they tried to figure out what are instabilities that are driven by dissipation in the system. That was one direction. And so if you go to the fusion community or the laboratory community, you will find this linear tearing theory literature very well developed, and it brings in mathematical boundary layer theory. Boundary layer theory is a theory, if you don't know already, it's an asymptotic theory where derivatives change very, very sharply in small regions and the functions themselves don't. So you can divide the problem up into two regions, an outer region where the derivatives are weak and a boundary layer where the derivatives are very strong and rapidly varying, and match the two regions. So it's a technique in asymptotic methods in applied math. A lot of the work that went on there, I hinted at by talking to you about islands and resistive instabilities and things like that. On the other hand, if you go to the space and astrophysical community, people were not thinking linear. They were trying to explain big things like flares, which release an enormous amount of energy very quickly. And so a compass for our thinking on magnetic reconnection that is nonlinear was set by a plasma astrophysicist or a space physicist. He calls himself a solar physicist, that Eugene Parker. And in fact, before Parker, even Sweet got to it. And they were actually asking this question. We know that flares liberate enormous amounts of energy. How rapidly do you release this energy? So you could say, let's look at the effect of dissipation. Well, if you just do plain dissipation, you don't get a very rapid time scale. So what they suggested was that your field lines that are pointing in opposite direction, this configuration, a very simple two-dimensional configuration, and imagine you bring the field lines together. Okay? Reconnection occurs. They first assumed that the system does so in a steady state manner. That is, that you could set del t equal to 0 in the MHD equations, but keep the full nonlinear equations to calculate what the reconnection rate is. Assume 2D, steady state, for simplicity and compressibility, and classical Spitzer resistivity. You see this equation? E plus V cross B equals eta J. I'm not going to write, should I write in the blackboard? Curl E is minus del B del T, right? Should I write? I'm changing my mind. Should I just do a little bit of, can I have access to the board? I think they've gone probably, right? Just raise it. I just want to write that basic equation for you. And let me set to C equals 1. That's Maxwell, right? Are you guys with me? You know Maxwell, right? Of course you do. So if I take the curl of that, I get minus, I'm going to eliminate E from the problem by taking the curl of this equation. But J, let's write it simply as curl B. For those of you who are very fond of CGS, you can always put in 4 pi over C and all the factors you want. And so if you write the curl of B and you use the fact that del dot B is 0, then this becomes minus eta del square B. So therefore, right? So if you look at that equation, the only place where plasma physics comes in is this one, right? If you drop that equation, that's what happens in a conductor. Del B del T equals eta del square B. You put an initial magnetic field, it'll diffuse away. On what time scale will it diffuse? A time scale that is determined by eta, which is a very small number. Anyway, so this is the equation that I have written there. And being faithful to MKS units, put del T equal to 0, steady state. But you're not going to throw away anything else. And now you do a very simple scaling thing. You're looking at this setup. Imagine that the solar plasma is such, the field lines are gradually merging, reconnecting, moving on, and this is done in a steady manner. Del T equals 0. So this is 0. On the left-hand side, you have VB and a scale length. So V in times B coming in, and this is getting dissipated in the layer. So it's eta Spitzer, B, and there's del square, right? So 2 scale lengths here. But there is another scale length here too. So only one scale length really survives. That's delta, that's the width of this current layer. So this gives you a very simple symmetric equation. Are you with me, right? pure heuristics. But this is all that Parker did actually with Sweet. This is a continuity equation. But if density is uniform and incompressible, then density cancels out. So V in times L coming in on the large scale and being squeezed out on the small scale. Coming in, V in L, V out, delta going out. With me? Right. Now, as the plasma is coming in, this is a region of low magnetic field. That's a region of high magnetic field. So the magnetic energy that is coming in is then pushed out as kinetic energy going out. So half rho v square out equals the magnetic energy coming in b square over 2. So if you do simple inversion of this, you get that the speed with which the fluid are ejected out of the layer goes like the Alfvén speed. Do you know the Alfvén speed? That has been introduced, right, in this class? Anyone does not know Alfvén speed, then I'll actually introduce it. Okay, so you know the Alfvén speed. It's nothing. It's really the more or less the speed with which information propagates in a magnetic field line, if you think of it as a string. And that's essentially what it is, b square over 2. So this is VA. So what do you get from this? If V out is VA, then V in over VA is delta over L. And you can show by some further simple calculation that that delta over L using the energy dissipation argument is really given by 1 over square root of S, where S is called the Lundquist number, mu 0 LVA by eta Spitzer. This is a dimensionless number, and typically, if you plug in the resistivity and typical system size given by L and VA, is a very large number. In the solar corona, that number can go from 10 to the power 14 to 10 to the power 18. But notice that this goes like the square root of S, which is really the square root of the resistivity. Square root of the resistivity is a number much larger than resistivity itself. It's a fractional number. So therefore, this time scale is faster than what you would get out of diffusion. So that's the first thing you learned from SweetParker theory, that you are getting, if you want to call it diffusion, but really it shouldn't be called reconnection because that is what it is. This sort of a topology enables the destruction of magnetic fields on a time scale much more rapid than the time scale of resistive diffusion, which scales like eta. If you solve that equation that I just put down, if you balance del B del T with the diffusion term on the right-hand side, the only time scale you'll get out of that, like a heat conduction equation, will be one that will be determined by eta. This thing goes like eta to the half, much more rapid. However, if you plug the numbers in, you will find that this is like a year time scale for solar flares. Parker and Sweet knew that even though this is a correct theory, it could not account for the speed of energy liberation in the case of flares, which are much more rapid. Are you guys with me? Right? So diffusion does not work. Unfortunately, this great simple theory, and I call it a great and simple theory because the arguments leading to the SweetParker timescale are just done in half a page on a sheet of paper and has been verified thoroughly until very recently. Questions have been raised, and I'll talk about that too, about the correctness of the theory. But it failed, correct though it is, it failed to account for the problem that it was after the solar flare timescale, which is much more rapid. And why did it fail? Well, the problem is, as I was pointing out to you, that there is a ratio of delta over L, the thinness of the current sheet, the width, against its length, which is system size, which scales like 1 over s to the half. In other words, all that fluid coming in is being pushed out in a very, very narrow layer. And there's a geometric issue with the way this thin current sheet is set up on how rapidly you can drive reconnection. Very roughly speaking, the rate of reconnection steady state is simply given by a fraction of the Alfvén speed, where the width to the length determines what fraction you get. And that's a very, very small number for the corona. So Petschek in 1964 said, you know what the problem is? He grasped the heart of the problem, but then he produced a wrong theory for it. But he grasped the heart of the problem. He said, and I really want to give Petschek a lot of credit, because even though his theory was wrong, this insight persisted. And to this day is a correct insight, that if you want to get rapid reconnection, you need to take that current sheet and shrink it. Shrink it in such a way that delta over L become comparable. And so he said, set up things in such a way, through shocks and external boundary conditions, in such a way that you take this SweetParker current sheet and shrink it down where delta over L become comparable, then you will get rid of this awful dependence of delta over L scaling like 1 over s to the half and go much faster. So he cooked up a theory based on his understanding of hydrodynamic shock theory. And this is all analytical work, by the way. Back in those 1960s, we didn't have a lot of computers, and these guys were making major progress. So he said, I'm going to reduce this by crafting boundary conditions, and I'm going to get the reconnection rate go as tau A times log of s. So much better than 1 over s to the half. Plug in your huge S, you get a small number. And that was in agreement with flare time scale. So people thought, great. The reconnection problem is solved. What we really need to do, like Petschek, use external boundary conditions in such a way that you somehow manage to shrink this. And there were some initial crude simulations of very low Lundquist number plasmas. Remember, if you run a simulation with a Lundquist number of 100, there isn't a whole lot of difference between s to the half and log s. They're comparable, or 1,000. When do you begin to separate out diffusion from reconnection? Is when you go to s sufficiently high. That means your code must be resolving something of the order of 10 to the power 5, 10 to the power 6, at least, before you begin to see a clear separation between diffusion and reconnection. A lot of turbulent reconnection studies, and I'm not going to pretend I understand turbulent reconnection, though, because it's an evolving field and there is a lot going on, and I'm going to share some developments with you near the end of the talk. But the problem becomes very complicated if people start waving their hands and say, well, there is dissipation in the system, large dissipation, and so we're getting a lot of reconnection. It's not clear to me that it's very sharply defined what the distinction between diffusion and reconnection is in a turbulent system. People haven't found a good way of doing that yet. So you have to be very careful when you actually claim fast reconnection, because the thing that separates slow reconnection, which is diffusion time scale, from rapid reconnection, which is, say, in the SweetParker case, s to the half, is s itself, and your simulation must be large enough to separate it so that you can see the difference. Well, that's what actually ended up happening. People started running better and better codes. And there were rumbles in 1979, but the person who made the greatest difference is Biscamp, 1986, in a classic paper where he did very careful work with MHT code, and he was running at high simulations. And he made the following conclusion. He said, the Petschek model, widely used in the community, is not realizable in high Lundquist number plasmas unless the resistivity is locally enhanced strongly at the X point. In other words, you're running your code and you're developing these current layers which are intense. Go by hand running the code, and if you raise the resistivity to a large value by hand, you'll get Petschek-like rates. But then that's not the regime we are all interested in. The regime that we are really interested in, unless we play those games, is the high Lundquist number regime, where things are very, very weakly collisional. And he says, in the absence of such anomalous enhancement, the reconnection layer evolves dynamically to form Y points and not a Petschek-like configuration. So, this is well known in my own group. We did these simulations of the corona, and I want to show you. There are n number of pictures like this in the literature, and ours is only one. But since we did it, I'm showing you one that is most easily accessible. So suppose you start out with a coronal picture where you have a vacuum field, and you set it up to be an X point in the beginning. And then you start driving it through foot point motion on this. you very quickly produce a deviation away from the X point, these elongated structures. What do they remind you of? SweetParker type of layers where the length are much greater than their width. And that's controlled by, this was done with the Lundquist number of 10 to the power 5. And that's roughly about right. So even when you pre-biased the system and created an X point, which would tend to favor Petschek, right? Because Petschek was saying, this is the key to your fast reconnection. If you go like this, but the length is much greater than its width, you're going to go to slow reconnection, so do this. So great, let's start with a system which was like this in the first place. If you run the same simulation with 100 Lundquist number, you will not see this lengthening. It'll all look like a diffuse X point, and you can calculate Petschek-like rates. Or log S gives you a number of the order 10, less than 10. S to the half gives you 1 over 10. What distinction are you talking about at S to the 100? Log S and S to the half are not that well separated. But at 10 to the power 5, 10 to the power 6, you begin to see a scale separation, and this is what you find. In short, then, the Petschek model is not realizable in the high Lundquist number regime unless you play a game in your code whereby either for numerical reasons or otherwise, you get local enhancement of dissipation at that point, and we can get something like Petschek. Question?
If you were to allow for slow reconnection and allow for X point formation through external somehow, how does the energy dissipation change for different angles at which reconnection happens?
The dissipation, as you know, if you calculate it using MHT equations, goes like eta j square, E dot j, roughly, right? So if E is roughly eta j, then it'll go like eta j square. So really the dissipation depends more on how strong the current density is in that region than the tilting of the thing. But if tilting is associated with some stretching, then you could have the same current distributed over a longer layer, and you could begin to see some changes in dissipation. So in the SweetParker problem, think about it. Eta j square. J scales like b divided by the width. The width scales like eta to the half. So if you square it, the eta cancels out. So in the limit of low resistivity, eta j square is independent of eta. That's volumetric. And then you integrate over the volume, depending on how large your volume is. So if you get a SweetParker current sheet, which is very intense, scales like b over the width, which is narrow, eta j square can be very large, can be independent of eta. And that's attractive because in the high eta regime, you're beginning to get a result that's independent of eta. But there's another issue. How much time do I have? Okay, I should go a little faster. Steady state models have a big problem. You said del del T equal to 0, but flare is not steady state. The sun is quiet and bang, it goes, right? So there's an impulsiveness in the process. So any theory which pretends to account for a flare-like phenomenon or gamma ray bursts or whatever has a huge challenge. The challenge is that you might explain the quiet times along with the active times. Somehow the magnetic configuration rests for a long time and then bang, it goes. What accounted for this sudden onset? So the magnetic configuration evolved slowly for a long period of time only to undergo a sudden dynamical change over a much shorter period of time. And this dynamics is often characterized by the presence of this current sheet. So the burden on reconnection theory is not just to get a fast time scale. You must go like this, right? So I therefore claim that steady state theories never had much of a prayer anyway, because they give you only one time scale. Whereas what you need to have is a theory that will go from DDT very small and then DDT very large. For some reason, this topology moves along and then bang, it goes. What causes the bang? Well, example, I'm showing these because you could get enough data from solar and stellar flares as well, but I'm going to talk about magnetospheric substance because we know more about them. This is the cartoon. What happens in magnetospheric substorms is the solar wind turns southward. you get reconnection between magnetic fields, flux gets transferred, then something happens with reconnection, and this side, the plasma dynamics evolves, and you get auroral brightening. And people have beautiful pictures of the aurora. And what typically happens is that those field lines come around and hit the north and the south pole, and you begin to see a brightening of these. And these were taken first by beautiful camera pictures by Lou Frank and others at the University of Iowa. And you see a sudden intense bulge of the auroral oval signals the start of an auroral substorm. And it forms close to the midnight sector and characterized by rapid poleward motion. And let me show you this. Here you see this brightening and see how it is spreading. This auroral arc intensification is all the signature of an Earth's substorm. And what you have is a quiet arc which brightens. But then as it evolves in matter of time, it becomes more and more intense and then eventually subsides. So if reconnection is driving this whole process, Sasha's thesis was a study of auroral brightening in pulsars, and he found that general relativity plays a very important role. But in my mind, if reconnection is playing a role, of course, general relativity is very, very interesting at that level. But on the other hand, this sort of brightening, you do not have as many pictures, nice pictures of this, of course, at pulsars, but there is a generic analogy between the two. One needs somewhat more complicated equations, but even this phenomenon for which there are so many constraining observations, we do not understand very well. And one of the observations that I want to draw your attention to is been in the field for a while. 1992, and what Otani did was that he looked at how the current density in the Earth's magnetotail changes as a function of time during the development of a substorm. So let me explain the coordinate system first. This is your x and z, and y is the direction perpendicular. This is a little weird because laboratory people like to make z the direction perpendicular to the paper, but magnetotail people call y the direction perpendicular. And what Otani said, he drew schematically a picture on what actually occurs during a substorm. He showed, in fact, that at distances at about 10 Earth radii, the current density goes through a slow algebraic period of growth for 30 to 45 minutes. And then, over a very short period of time, there is a sudden enhancement. And then a relaxation where the current disrupts completely. The plasma just sheds it in violent upheaval, relaxes to a dipolar state, which is nearly the vacuum field. And it's called depolarization for substorm phenomena. And this time scale is about 10 seconds. 3 time scales in the problem. So when I started working in the field, I told myself, it's not enough for me to come out and say, I can get something that goes very rapidly. I have to explain why this happens. And then that, and then the relaxation. All 3 time scales should come out from a theory, which is a good theory. So this is agreed upon in the magnetospheric community and is a stringent criterion on instability theories to do this. And I can tell you, resistive theories goes nowhere with it. Unless you play games with the dissipation coefficient. The code is running, you suddenly go and throw a lot of resistivity and expect a sudden enhancement, and then you take the resistivity away, that sort of a thing. But if you want your theory to be self-consistently right, you don't want to do that. So we realized pretty early that, look, as it is, MHD is very suspicious for the magnetosphere. People run it, and for large scales it's okay. But we know that the magnetosphere has 1 particles per centimeter cube. If you calculate the mean free path of that system, it easily is larger than the system size. It's largely a collisionless system. And, you know, in MHD theory, we have we take the simplest form of Ohm's law. This eta is nearly 0 for the Earth's magnetotail. This V is really the single fluid velocity. But if you think about it in terms of ions and electrons, this V is mi Vi plus me Ve divided by mi plus me. But me in a hydrogen plasma is much smaller than the ion mass. So V is approximately Vi. So MHD theory, really, the V that sits in there is almost the ion velocity. But MHD doesn't make a distinction between electrons and ions. So if you want to ask yourself what is the right equation for right Ohm's law in a system where there are ions and electrons, you go to the electron equation of motion. That's what the generalized Ohm's law is. It's essentially an electron equation of motion. So what I have done is simply put the inertial term on the right-hand side, pressure tensor, J cross B. In fact, if I rewrote these equations and move this term, it will look like the electron equation of motion, just inverting the order. So you can kind of see what's going on. And the VE cross B that sits there in the electron equation is broken up when you write J as NEVI minus VE, eliminate VE from the problem, write things in terms of VI, and you get this term, and you get the Hall term. So origin of the Hall term in the generalized Ohm's law is that you simply rewrite the VE cross B term in the electron equation. So we're going to start with that to try to understand. 1 over 5, so we just do some simple scale lengths. I'm just going to give you the results. And by the way, you will say, why aren't you calling this S? Because this length L is sometimes a point of confusion, may or may not be the system size. So when you read turbulence books in MHD, or people keep this script L and they're thinking about a system size type, but in Parker's definition, that L was the whole length of the current sheet. So think of S as a special case of Rm. It's the magnetic Reynolds number. 1 to 2 is this ratio, system size over, this is called the electron skin depth. 1 to 4 is the ion skin depth. And 1 to 3 is this L over rho I. Typically speaking, you can see that eta J sitting here, I'm not even going to worry about this any further, not much more anymore going forward, because as I was telling you, that in the Earth's magnetotail, you will find that this term, treated very generally here, is really too small to matter. So really, you're back to electron inertia term, pressure tensor terms, and remember what I told you? All the terms for which the curl is non-vanishing can break field lines. Electron inertia can break field lines. This is what happens in particle and cell codes. We do not have collision operators. What breaks their field lines is electron inertia, and Sasha and Lorenzo did pair plasmas with you, I'm sure of that, where me is equal to mi. So you don't have two skin depths, but only one. C over omega p I is the same thing. What is breaking their field line is particle inertia, and it is every hydrogen plasma peak theory's dream to run their codes at m equals mi at not m over mi of 1,836, because if you do that, the problem becomes so much easier numerically, because you don't have to resolve the mass difference and the scale lengths that go with it. So for the magnetosphere, though, that separation is very important, and the state of the art of the field right now is that we can run 2D simulations of reasonable sizes on the supercomputers with realistic mass ratio, but we cannot do that for three-dimensional systems of reasonable size. And even the exascale computers of 2021 will not give us access to that regime. So doing realistic plasma parameters still remains somewhat of a dream of the future. On the large scales, all of these terms are, you can put this to the left-hand side, all these terms are small. And this is why ideal MHD is very good on large scales. But in small scales, when you're getting into these thin current sheets, all these terms matter. And the reconnection rate is actually controlled by what happens. If you write this out in dimensionless form now, a simple form of it would be this, where I've thrown away the resistivity term. I've assumed that the pressure tensor is actually a scalar, and I've thrown away the electron inertia terms, excuse me, and I'm talking to you about Hall MHD, which is actually, sorry, I misspoke. I misspoke on a number of fronts. Let me correct myself again. What I'm trying to do here is that I want to understand what goes on if I put in non-ideal terms in Ohm's law. And we understand what happens if you put in resistivity. You get SweetParker theory. And you're asking yourself the question, how does SweetParker theory, which fails to explain this rapid onset, change if you put in collisionless terms? So I'm asking that question here, written down a generalized Ohm's law, which has the Lundquist number, the electron inertia term, and the Hall current and the pressure gradient of the electron, with the further assumption that the pressure is a scalar. This is what is called Hall MHD, because it has the Hall term in it. It also has the pressure gradient term in it, and the effects come in very similarly. This is what we learned doing Hall MHD simulations, and this was a criterion that I developed with some postdoctoral colleagues and students of mine back in the 1990s. And what we realized was this, that the SweetParker layer has a width that goes like L over S to the half. Now imagine you start out with a plasma with a current sheet like this, and gradually the current sheet is thinning down and you're forming a SweetParker layer. If it so happens that the SweetParker layer width falls below the ion skin depth, you will see a sudden onset of a new fast reconnection phase that is not there in the SweetParker theory. The answer is a little different if you have a guide field, which means the field perpendicular to the plane of the paper, in which case this criterion, C over omega pi, gets revised somewhat by the multiplication of beta. But that's a minor matter. Basically, what you're looking at is when the SweetParker width in the system falls below the ion skin depth, you should see a rapid enhancement of the reconnection rate. Let's set up a simulation. Remember the Harris sheet that you've already seen? Imagine you have a field perpendicular that you could change, 0 or not, to look at both limits. And you drive the system gently with some flows coming in. Are you guys with me? Right? What happens to this system in the SweetParker case? You know the answer. That's what it looks like. And by the way, now I'm actually doing the lab coordinate system. I apologize for the switching back and forth. Z is now the plane perpendicular to the paper. Look at this thin current sheet, extended, and EZ is like eta JZ. That's what you expect from SweetParker theory. They have no scale separation. Both magnitudes are different because there's eta multiplying this and this. And the jet that is coming out has this sort of a structure where the fluid is being forced out of this narrow layer. This is what gives you the SweetParker rate. What did Petschek teach us? There's no way you're going to get fast reconnection if you have this sort of a system size where the width and the length are very disparate. Well, guess what? For the same initial condition, if you turn on the Hall current term and run exactly the same simulation, transiently the system looks like this, and then it begins to look like that. It goes through a very major geometric readjustment whereby the current sheet goes from that extended Y-point type structure to this X-point type structure. The jets open up, giving you much higher rate of reconnection. And if you look at the electric field, EZ is not like eta JZ. The scale length of EZ is much broader than the scale length of JZ. Look at it, how wide this is here and how narrow JZ is. The physics says that JZ is actually controlled by your dissipation mechanism. In this particular case, it could be resistivity or electron inertia or whatever. And that lives on a scale length of either the SweetParker layer or the electron current skin depth, whichever is your mechanism breaking field lines. But the electric field is on the scale of the ion skin depth. This scale separation, it will vanish if you go to an electron ion plasma, to a pair plasma, because there's no separation between electron skin depth and ion skin depth. But in a hydrogen plasma, you actually have a multi-scale problem in that the current layer is much narrower than the electric field is. And the jet opens up, and you get a rapid enhancement in the reconnection rate. And this is shown in this plot where you're looking at the log of how the flux function is changing in time. In the SweetParker layer, first of all, you look at the current density. The current density actually, this is SweetParker, resistive SweetParker. This is Hall. The current density is going up much more rapidly. What do you see? You see up to a certain point in time, the resistive and the Hall results are the same. And then when this criterion happens, that the width of the current sheet has fallen below the ion skin depth, the Hall terms immediately kick in, and you get a rapid enhancement of the reconnection rate. This is what you see in the flux decay as well. It's slow in the nonlinear regime. Look at how it has taken off. This is onset. This is the onset of rapid reconnection. So therefore, our explanation was, if you start out with a system with a diffuse current sheet, in the beginning you have SweetParker type of reconnection, until it so happens that the width of the current sheet falls below the ion skin depth. As soon as that happens, the Hall currents and or pressure terms will kick in and will give you a rapid reconnection. And if you run particle in cell simulations, we did Hall MHD simulations, but you could run full PIC simulations. Here are the field lines, electron flows, ion current density, electron current density. Look at the scale separation between the electrons and the ions. And you can actually, you therefore see this current density is calculated by NeVi, being the ion fluid velocity. What you're really seeing is the separation in scales between ion fluids and electron fluids, which is absent in MHD. They all move together unless they come to the resistive layer. But what happens in these problems is that your reconnection layer is this. There's an ion scale, and there is a buried electron scale. So it's really a multi-scale problem, as is the title of this summer school. Of electron scales and ion scales, then coupling to the larger MHD scales out there. This is not just, one of the advantages of working in the Princeton Plasma Physics Laboratory is the experimentalists don't believe the theorists. And they make it their life's mission to prove that the theorists are wrong, which they often are in plasma physics, I say very humbly. Because in a field which is as driven by observations as plasma physics is, experimentalists in laboratories certainly have been a step ahead of us in terms of proving us wrong. Well, in this particular case, we actually predicted something that the experimentalists verified later. And I remember Masaki Yamada, who's my colleague at PPPL, told me, this criterion you have, I don't really believe it unless I see it. Well, what he did was that he did an MRX experiment lab, and he set it up in such a way that by controlling the density of the plasma he puts in, he gets a filling pressure in there that determines his Lundquist number. So he sets it up and tries to get a nonlinear reconnection rate, and this is what he calls the kind of the SweetParker layer. His Lundquist number, unfortunately, is not as high as you would like. It's more like 10,000 or something. But then what he did was that he did another set of discharges with density low, which took him to the Hall regime. And look, clear shrinking occurring in the Hall problem as opposed to the SweetParker layer where the current sheet is broader, but you get a shrinking effect. He measures the reconnection rate. It's about what theory predicts. So this has also been done, by the way, by Jan Eggedal. Otherwise, Harsha is going to get angry with me. Her advisor, he did this in MIT too. He checked it out for collisionless systems, and he verified that there is, in fact, this onset mechanism brought about by Hall. Yeah.
So the change in the aspect ratio looks like maybe a factor of 2 or 3.
Yes.
That's what you had.
That's what you have, exactly. So unfortunately, you don't, MRX has a system size limit. And so you're right, it's a factor of 3, but he did see the difference. It would be really nice to do a larger experiment, which is what the new experiment FLARE is going to do in Princeton, and that's now under construction. And it's precisely to get around this problem that you say, namely, it would be really nice to get a separation between the system size. But this criterion, if we say di over delta sp is what determines whether you get rapid reconnection or not. So here is MRX, here is tokamaks, magnetosphere, solar flare, ISM, protostar. It turns out the ISM is one case where this condition is not obeyed. So I don't know whether you could get fast reconnection through the Hall mechanism in ISM. In ISM, actually, the ambipolar diffusion term, neglected in our theory, could play a very important role. And this is what I hope to work on with Bhishek Manek while he is here, that if we change the Ohm's law to actually put in ambipolar diffusion term, how do all these things change? But at least this mechanism would seem to have a hard time operating in the ISM. But this tells you the story, lambda mean free path over L. And so if you go to collisionless systems where lambda mean free path over L is becoming larger and larger, the Hall effects and the pressure gradient terms are going to become more and more important. And so it's just a continuum of things. So how about this magnetotail problem that I set out to say I must solve, right? So we said, let's therefore run a Hall MHT simulation of what is going on in the Earth's magnetosphere. So this is the magnetotail, and we're looking at the current density perpendicular. You start out with time t equal to 0 with a dipole field, and you drive it very gently with the electric field. You get this thin current sheet, and you monitor what the current density does at a distance of about 10 RE. What we found, in fact, is that for Lundquist number about 10 to the power 6 or so, we really do get this slow phase, and the onset occurs when the ion skin depth obeys that inequality, reconnection rate jumps up, and it disrupts. However, in this 2D simulation, we found that this fall off takes about 10 minutes, which is an order of magnitude higher than the observation of 1 minute. And therefore, I consider that 2D simulations of this type are adequate to explain the slow growth and the onset phase, but not the disruption phase. Three-dimensional effects, other plasma instabilities, pressure-driven instabilities, which are very important in the system, which break the symmetry, are going to be very important. So right now I'm working with Samuel Totorica, who is a postdoctoral fellow at Princeton. He came from SLAC, he's a student of Roger Blandford's, who is actually now doing this simulation with a full PIC code in 3D in large computers to take into account 3D pressure-driven instabilities that are excluded from this treatment in order to understand this 1 minute drop in the time scale. Okay, so how am I doing with time? Still 20 minutes. Are you guys too tired? Now comes the really exciting part 2, about why everything I said to you has now to be changed. I'm not very happy about that, but it led to some new discoveries. This has to do with this plasmoid instability of large-scale current sheets. So you see, I was extremely happy. You know, when you grow older, you want to feel like after you finish your career, there's at least one problem you settled, just one. It would be nice, right? So I told myself that if I could settle with my students and postdocs, I should always say we, because really I'm growing older faster than they are, and like to think that together we did solve one problem. So we actually thought definitely solve the onset problem and reconnection. There's all this experimental data. We have this neat criterion, extremely simple, tested out by simulations. So what you do is that you start out with a thick current sheet, you wait for it to thin down. When the Hall effects or pressure tensor kick in, you get rapid onset. We know how to go from slow to rapid, right? Wrong. Wrong because what we overlooked was that this tendency to form these extended current sheets over a long period of time in the manner in which Sweet and Parker told us was itself wrong. Sweet and Parker assumed that you have an extended current sheet that is stable over system size lengths. But is it? Well, it took computation again to bring us, but I should tell you a little story here. This is why graduate students are so very, very important. I went to this workshop in Cape May, and Nuno Loureiro, who is now an associate professor at MIT, had a calculation where he was claiming that a thin current sheet will have a linear instability in it. And the linear instability didn't look like anything that I had ever seen in resistive stability theory that was developed by Fortkillen and Rosenbluth. He had this funny growth rate. That the growth rate would go up with S of the Landquist number as positive power. And I first saw it and I said, no, there's something wrong here. And I didn't believe him in the beginning. But then when I went back home, 2 days later, I knew he was right, because I went back to the Fortkillen-Rosenbluth dispersion equation, which I knew very well. And I realized that Fortkillen and Rosenbluth always analyzed a Harris sheet whose width was A, some sort. What Nuno was doing was to look at the stability of the SweetParker current sheet whose width was dependent on the Landquist number, because the width goes like 1 over s to the half. To treat that boundary layer problem, you'll have to rescale the equations. So I went back and simply did half a page of calculation to the dispersion relation of Fortkillen and Rosenbluth, did the scaling, and I had Nuno's answer. So the answer, therefore, was that Nuno was right. There is a linear instability in the system, which they hadn't discussed, simply because they were dealing with a current sheet in which the width was some system size, not dependent on the Landquist number. But a SweetParker current sheet depends on the Landquist number, goes like s to the half, and therefore has a fast instability. But Nuno's theory ended there. Very rapid linear instability. It immediately suggested to me that if you go nonlinear, something was going to happen to that layer, and we're going to get out of SweetParker scaling. Except I didn't know what the answer was. My guess was that it was going to have a weaker dependence on the Landquist number. So in my own group, we had wonderful colleagues who have high-resolution simulations like Emin Wong, Honggang Yang, and others. And I want to just show you a picture. Here is a thick current sheet. Now, this is pure resistive MHD, okay? Thick current sheet, slowly relaxing, 2D, see what happens. Comes down, thins down. And if you look at this, this is going more or less like SweetParker theory. But look what happens. That extended current sheet immediately starts breaking up into secondary islands like this. Large islands move slowly, then smaller islands, they're eaten up. And the way this happens is that large islands and small islands are like current filaments which attract each other. So they tend to merge by what is called the coalescence instability till the system goes through and chews up the whole flux in the system. And this happens in an extremely time-dependent manner. If you look at Nuno Loureiro's PhD thesis, he imposed right-left symmetry, and the plasmoids couldn't move. So what he saw was a rapid instability, but then nothing happened. But if you relax left-right symmetry, things can go very unstable, and you chew up the whole flux this way. And I should tell you, and I don't want to dwell on this, if you go back to the literature, going back to the Russian literature, Russians do everything analytically before anybody else. So go look. If you're doing a plasma physics problem, Sasha is laughing. They don't do computer simulations. They do everything analytically. I'm sorry, I'm oversimplifying. They do, of course, but they're way ahead. 1979, Bulanov was saying, you know, these thin current sheets have secondary instability. But his growth rates were not quite right. Doesn't really matter. There was enough in the literature that will make you think that the SweetParker assumption of an extended current sheet that should not be stable, there was stuff like that, right? But only Nuno Loureiro first calculated this growth rate correctly. Thereafter, the nonlinear work showed, and what it came out eventually is that after Nuno's linear work, we did the nonlinear work, and other people have done PIC work, Hall MHD work, common theme. No matter what the level of collisionality in the system, you have this reconnection rate, and this is from our paper. If you calculate the reconnection rate, what happens is that up to 10 to the power 5 or so, the time of reconnection goes up as s to the half, as predicted by the SweetParker theory. But once you crossed 10,000 at 10 to the power 5 or whatever, you get into a new regime where the reconnection rate becomes independent of resistivity. How does it go? It goes like 0.01 VA. Beyond that, you can change Landquist numbers whatever you want. And this the astrophysicists really would like, because all their codes have dissipation that is limited, MHT codes especially. But if the reconnection rate via the plasmoid instability really becomes independent of the dissipation, that's good news. That means you don't have to track, as long as you're over a certain threshold, and as long as you have this. But why was I saying that this created a problem? It created a problem for me and for those who believed that the transition from SweetParker to C over omega pi width gave you a sudden onset, remember? Now what am I telling you? As soon as you get the thin current sheet to form, it'll go unstable to the plasmoid instability. Way before the Hall effects kick in. So the thin current sheet then will not have as much of a growth phase. All that you need to do is to create a thin current sheet, bang, it'll go. So what happened to my 30 to 45 minutes of waiting till the Hall effects kick in? Well, I'm waiting for Godot. I'm not going to get there. It's going to go unstable before I get there. So while we discovered a new instability, we screwed up our onset mechanism. And that's where we are stuck now. What I'm worried about is, how are we going to have a phase in a system where this solar flare picture, right? Where we store a lot of magnetic energy and then we release it. Our answer was store magnetic energy in the SweetParker slow phase and then release it. Now we find that the SweetParker slow phase is very short-lived due to the onset of the plasmoid instability. Do you guys get this, right? We get the fast onset now, but we have too little time to store energy. Now, in the Earth's magnetotail, maybe this is not a problem. I'm trying to think of ways of getting around it because it takes a while to get a Harris sheet to form, something like this. So you could say, well, nature, doesn't come prepared with Harris sheets. First, you have to get the magnetic configuration where you have nice topology set up, and then this will happen. Maybe that is an answer. But I don't want to pretend to you that this is a problem that is solved. As to whether we can understand this result, I'm running a little short of time. But what you can do is to come up a very simple heuristic argument, which I don't have the time to go into, but my slides will be available and you can go through it. Essentially, we can demonstrate that there is a reconnection rate that scales to the SC to the half, where SC is the critical Lundquist number for triggering the plasmoid instability. That's typically 10 to the power 4. So we can explain this 0.01 VA result independent of resistivity by essentially using a variant of the SweetParker argument, but taking into account the fact that you have a plasmoid instability. This instability led to a new phase diagram for magnetic reconnection. And in fact, TREX, FLARE, a number of high energy density physics experiments in the laboratory now organize the plasmoid instability has made a qualitative difference to our understanding of how reconnection proceeds. If you plot the axis of L over di versus the Lundquist number, you have different regimes, the old SweetParker reconnection and the Hall reconnection. But now, because of the plasmoid instability which kicks in at about this point, you have plasmoid-mediated reconnection occurring at a very important part of the system. In fact, most astrophysical systems are really in the plasmoid-mediated reconnection regime. There is ample evidence for this already in the simulations. And the simulations are getting way ahead of theory. And it'll be really nice to get further and further. I'm speeding up just a little bit here to tell you that resistive Hall MHD gives you these plasmoid instabilities as long as you cross the threshold. This is PIC simulations, no collision operator at all, very similar plasmoid structure. The theory for the fluid case is much better developed than the collisionless case. There's a lot of analytical work, both in linear and nonlinear regime, that we need to do to make sense of these beautiful results. But theory, there's a lot of serious work to be done, a lot of analysis to be done to make sense of these results. In fact, this was work done by one of my postdoctoral colleagues many years ago, looking at cluster data. What she did, cluster, as you know, was 4 satellites going to the Earth's magnetotail. And by doing clever detective work, she could actually count the number of islands that she could measure. And her premise was that the extended magnetotail current sheet, due to the onset of the plasmoid instability, will have many, many islands. And in fact, she found, through measurements of electron bursts and energization, 10 islands within 10 minutes using cluster data. and is very clever detective work. I don't have the time to describe to you, but she looks at particle distribution functions. Nearly all of them are non-Maxwellian, putting to lie any MHD models we might want to use. And what she noticed furthermore, and this was an important point, is that due to particle acceleration, she got particle energization in all channels. But a particular discovery that she made was that the most energization actually occurred not at the X points of the reconnection, but at the O points, at the center point of the islands. And this actually, in a way, inspired Drake and others to suggest that if you have a lot of magnetic islands in the system, they will provide very effective acceleration mechanisms. And I'm sure you've seen Lorenzo Ceroni's work yesterday where he talked about what the plasma instability can provide enormous particle acceleration as well. He's done a lot of work on spectra and so on and so forth. These islands, driven by the plasmoid instability, be it in collisionless or collisional systems, can be very effective agents of acceleration in a way for which we have abandoned numerical simulations and not as many analytical theories. The 2D theory is getting better and better. People have done measurements. If you think of density blobs as plasmoids, people have done counting of these things in the post-CME current sheet. My former graduate student, Ligia Guo, has done very nice work on this. A really important question that I want to end this talk with is, a lot of this work that I presented to you was 2D, but what about 3D, you would ask? Well, what happens when you go to 3D is that this is a Jackson Pollock-like painting almost. You get this flux tubes, right, coming out, but if you break the symmetry directions, then the magnetic fields along the direction perpendicular start to overlap. Field lines become very stochastic and turbulent. So plasmoid instability starts out 2D-like, but then quickly evolves into a 3D mess of the kind that you're looking at, produces turbulence. What is the nature of this turbulence that you get out? Self-driven. This is not like the classical picture of Kolmogorov or Goldreich, Sridhar, or others, whereby you put in a magnetic field and you put noise in the system and you let the system evolve in time. This is self-generated. Plasmoid instability occurs, it then produces this, and you're looking at kinetic energy, magnetic energy, and these are the areas where reconnection is extremely strong. If you look at the 2D projection of the 3D run, you'll still see remnants of that structure. In other words, what we are doing here is that we start with a 2D system, it goes 3D, then we average in the third direction and make plots of the mean profiles. And there's some remnants, but if you look at the third direction, it's very turbulent. So it's a softening. You see plasmod-like structures still persisting, but really it becomes a harder and harder case to make that you have anything like this. And if you go back and calculate what the reconnected flux is, and the way we do this is that we calculate an average B field by averaging along the z direction, defining a flux function for the mean field, and looking at how the rate changes, what you find is the 3Dness doesn't change your reconnection rate all that much. You still get something like 0.01 VA. And in this respect, our findings are very different from Lazarian's findings, who has argued that if you do turbulence simulation, you get a rapid enhancement going up to 0.1 VA. We don't have those results. Of course, our initial conditions are not the same, but in this case, what we find is without collisionless effects like Hall or Pick effects, the average reconnection rate in resistive MHD to us remains about the 2D rate, which is 0.01 VA, which some may argue is not rapid enough. In those cases in some cases like the chromosphere, it may be completely fine. But if you need 0.1, resistive MHD theory, according to us, doesn't give that to you. What is going on in these systems is that 3D mean flow is similar to blurred SweetParker. Turbulent reconnection is enhanced reconnection rate by broadening the outflow jets. And I want to make a distinction between, so you see the jets, they're broadening. And that's what accounts for why you're getting this sort of reconnection. But it is not like a simple enhancement of the resistivity. But if you go back and look at the current density, even in a turbulent system, it doesn't broaden. It is not like eta has become eta anomalous, and therefore the width of it has spread because of the anomalous enhancement of resistivity. What is really interesting is that the current sheet remains this thin structure. The jet becomes like this. So if you think of the dynamo, whereby you take the mean electric field and you average it, you get this term, which is like a dynamo-like term. I'll talk about dynamo theory in the second part, so you'll understand this a little bit better. But this does not mean eta A Jz, so that eta can simply add on to eta A, give you a larger resistivity and a broadening of the current density width, and hence the faster reconnection. Current density width is not changing very much, but the reconnection rate is going up. So this is something that we are looking at. If you look at the turbulence, these spectra that we calculate as functions of time don't show any of the classical 5/3 or 3/2 signature of the kind that goes on in the classical turbulence theories. So we have deviations from Goldreich-Sridhar spectra. I don't know whether Berkeley mentioned it in her lecture to you. That did she mention turbulent MHD spectra at all in her lectures? She said to me that she would. So I'm assuming that she may have at least just introduced the notion to you that in the presence of magnetic field, hydrodynamic turbulence, well known to be Kolmogorov, becomes very anisotropic. The structure parallel is very different from the structure perpendicular, and Goldreich and Sridhar developed a theory in which they argued that you actually get a Kolmogorov-like spectrum k up to the minus 5/3. The exponent remains the same. This, however, was challenged by Boldyrev, who's done an equally convincing theory to argue that effects that Goldreich-Sridhar left out actually gives you k up to the minus 3/2. Whatever it is, minus 3/2 or minus 5/3, you can see that this spectra don't correspond to any one of those. These are highly inhomogeneous, inhomogeneity-driven turbulent systems where you start out with current sheet-like structures that produce twisted flux rope type structures that then overlap and produce turbulence. And the spectrum is something that is not easily obtainable. I'm getting to the end of my talk, but I want to just mention one thing to you is that you could ask, how does the plasmoid instability change our pictures of turbulence? And I'll just make a couple of remarks and I'll stop there, which is that typically in hydrodynamic turbulence, you have a stirring range where you're forcing the system, an inertial range, which by the classical arguments of Kolmogorov have a spectral property of k to the minus 5/3, and then a dissipation range, typically controlled by viscosity or whatever it is that you have in a hydrodynamic system. In a collisionless plasma, it is widely believed that that inertial range breaks eventually at a kinetic scale. And the kinetic scale could be an ion skin depth. Beyond that, there is electron skin depth. So the MHD scale occurs only over a certain range until dissipation comes in. What the plasmoid instability has done is to introduce a new scale length in the problem. And the scale length is that when you form extended current sheets and is interrupted by plasmoids, then that becomes the length scale at which this current sheet is beginning to disintegrate, without even waiting for Hall effects or pressure tensor effects or anything. Have we calculated that? Luca Commisso, when he was a postdoctoral colleague in my group, actually analytically worked that out. And he found that due to current sheet presence, what you will have is you'll begin to see disruption of the current sheets. And this particular width, K critical, is determined not by your dissipation, but when the plasmoid instability onsets. He has made a prediction in 2D and 3D. And what I want to simply tell you is that we've done 2D simulations, and I can't go into it's published as a physical review letter, but we did a high resolution simulation. And what you will see is, in fact, if you blow up these small regions, you see plasmoids. You can do it at Rm 10 to the power 6, or you can do it at Rm much lower than that. You compare the spectra in both cases, and you find that there is a difference. And this is, so in other words, when the plasmoid instability onsets, where the break actually occurs appears to be controlled by the plasmoid instability. When it does not, it's the dissipations that come in. And so Chuan-Fei Dong did this simulation in our group. one at 10 to the power fourth where there were no plasmoids, another when there were plasmoids, and the results are different. And this is what he showed, that in fact you get a new spectral range when you actually have the onset of the plasmoid. But this is all 2D. To do this in 3D would take exascale computer to do it. We'll probably do it in 2021 when we have access to Aurora, the first exascale computer, which will allow us to do the same simulation in 3D. That's the end of the story as far as reconnection is concerned. I should tell you about Sisyphus. In my mind, magnetic reconnection is the Sisyphus of the plasma universe. It's always pushing things up the hill. Things self-organize and it comes coming down. And so I was in Paris and I went to this museum and took this picture. And so if you are in Paris, you read Camus. The struggle itself is enough to fill a man's heart. One must imagine Sisyphus happy. Reconnection continues to do its job. Thank you all very much. Perfect timing, huh? Or not, I don't know. Questions? Yeah.
And when you mentioned this, like extended MHD, I remember seeing somewhere where there's kind of other versions of these flex freezing, but just not with the magnetic flex, but there's some kind of like modified flex, like V plus some vortice or curl. I forgot exactly what it was, but is there kind of any analogy or implication of this other flex freezing when you don't have dissipation, I guess, but you might have like the Hall term or other things?
So Alfvén's theorem is flux freezing, as you know. The question is, what breaks Alfvén's theorem? And the Hall term, if you want to ask, if looking at it just a little bit deeper, is that let's focus on the Hall term. But J is and Vi is in fact V, very roughly speaking, as I just indicated if you take into account. So you can rewrite that equation by moving it to the right and using this relation, whereby it will become E plus VE cross V equals 0. What that means is that the Hall current leads to electron freezing, but not ion freezing. So you don't really break the frozen in flux condition at the electron scale, even when you have Hall. Hall is a funny and subtle thing. It enhances the reconnection rate because it enhances electric field, but it does not change the fact that you need something like resistivity or electron inertia, or some would argue turbulence, to break flux freezing. So I didn't I was just telling you about, so whatever you say about Alfvén's theorem with E plus V cross B equal to 0 goes over to E plus VE cross B equal to 0 when you have Hall effect in. So it simply moves all of Alfvén's theorem to the electron scale. But you have to go and do something on the electron scale, like a pressure tensor or particle inertia. That's what Pick codes do. And that's why you have reconnection going on there. Are you with me? Yeah. And Gregory Ink has written a Nature paper. I still don't understand his paper, but I'm reading it still. He argues that if you have enough turbulence, nothing matters. Hall current, particle inertia, you'll always get some kind of a universal reconnection rate. He calls it Onsaga's theorem or Onsaga's conjecture, whereby the answer will not be dependent on microscales. All the simulations that we have done, we can quantify this. Now, they're not fully turbulent simulations, in fairness to him. It's very, very hard to run a very turbulent simulation and resolve all the small scales. I showed you a simulation effort where we are tracking plasmoid instabilities on really narrow layers to figure out how the dissipation range is modified. That's an extremely hard computation. So it's very hard to disprove him in a fully turbulent case. But it did make a difference to us what the magnetic Reynolds number was in the RM case. He would argue that turbulence makes this quite unimportant. So if you want to take the point of view that I can run this big astrophysical MHD codes and or collisionless codes if they would go there, and nothing really matters on how we break field lines, and the reconnection would somehow asymptote to some kind of a value, and that's all you need to know. I don't know what to say. I can't prove it, but our work doesn't indicate that so far. Unfortunately, it does seem to depend on dissipation mechanisms. You have some robust facts, like the Lundquist number dependence becomes very weak. But collisionless case is a very different case. We haven't studied that. Open questions.
In this plot that you had a few slides back, you had sort of a partitioning of the parameter space into what kind of mechanism you expected.
Yeah, the phase diagram.
Yeah, what was going on in, so why did you have this, it might help to see the plot.
Absolutely. Let's do that.
So why do you have this transition from Hall reconnection transition triggered by plasmoids to Hall reconnection that doesn't care about plasmoids as you change the length compared to the...
Okay, so what you notice is that if your system size is sufficiently small, then all you have, say suppose you're about 100, all you have are really the two regimes that I talked to you about. And then if the system size becomes larger and larger, you open up the phase diagram, making new possibilities. So I skimmed over, you're catching me on something that I skimmed over very rapidly because of lack of time. So remember I showed you the resistive Hall effects, and it breaks up into plasma. So now you bring in Hall. What happens when you bring in Hall is what I'm going to show you, something I didn't dwell on, is that if you look at this picture that I'm showing you, you see this A, B, C, I marked, but I didn't dwell on it. What were these runs? So let me now go in a little bit more in detail. A, B, C, and run D is this lower run, which is essentially sort of at the margin. What you see is that when you turn on the Hall effects, you get more rapid reconnection than the SweetParker layer was giving you. And what you're having is, you're having a competition between the plasmoid instability and the Hall effect that you have seen. Hall wants to speed things up by trying to contract the current layer to form an X point. What the plasmoid instability wants to do is to break up the extended current sheet and produce a whole lot of plasmoids. When the Hall effect dominates, what you have is an expulsion of the plasmoids out of the sheet, and the tendency to form this X point wins over. Now we are back to the classic Hall picture without plasmoids that discussed before. This troubled me because I thought to myself that maybe the plasmoid instability doesn't matter when you have Hall effects, because what Hall is going to do is going to try to make the current sheet into an X point and just push all the plasmoids out. But then when we ran our simulation with a much larger system size of L over di, this is about 800 di, L over di. You see the X point form? Do you see that in the third frame? But look, it's going unstable to plasmoids again. And this X point formation is a metastable state. It doesn't stay there, it forms plasmoids again. So it's a little bit like the PIC runs. If you do PIC, what you find is you get this extended current layer, breaks up into plasmoids. PIC has more physics in it than Hall does, because PIC has Hall plus pressure tensor and everything. And you ask yourself, is the plasmoid just showing up in the resistive theory and it just goes away when you go collisionless? Because our Hall runs tended to suggest, the smaller Hall runs, that all you care about is this X point eventually forms and the plasmoids are expelled. Not so. They continue to be persistent in the collisionless runs as well. That explains to you why, and I didn't dwell on it, and you're sharp to catch me, I didn't dwell much on this blue and green regions. There's a lot of action going on there, and you get to those regions only by designing experiments in the lab whichever L over di between 1,000 and 10 to the power 4, which is what MRX is about, flare is about. But in astrophysics, of course, that's where you live. I mean, you have lots of L over di is very, very large there. Any others? Okay, thank you very much for your attention. After lecture, it will be dynamo theory.